If no, let's go back to inverter, right? Inverter is the basic thing because for LAN gate, NOR gates, they are all inverter if you connect the input together, right? Or in certain configuration. So if we know how to analyze an inverter, then you will be able to do the rest well. Now, when we do this inverter, we will learn about the static behavior. What is the meaning of static? It means that the ramping time is infinity. You do it very slow, so you don't have capacitive effect. Okay, we learned that already. We already learned something called VTC, V in, V out, and the curve will be something like this, correct? And from there we learn VM, right? So someone tell me what is this? What do we call the output? Highest output, what do we call it?
VOH.
VOH, good. Right, how about the lowest output?
VOL.
VOL, thank you. How about this 2 point, which give us log -1?
VIH and VIH.
Thank you. Thanks for everyone, for those who also answering. Good, right? Now we want to calculate. How do we find those, right? Of course, you know how to calculate, just keep doing math, but we will have some approximation and insight, right? And hope that from those, you can deduce something, right? We talk about besides the function, we will understand the noise margin, and noise margin, we know that NMH is equal to VOH minus VIH, right? The noise marginal is equal to OL minus VIL minus VOL, correct? Did I say anything wrong? Right, and then propagation delay. You should be very familiar with this already. I keep reminding you because sometimes we just forget the definition, and that's why we always talk about from V in 50% to V out. Something wrong with that. 50% to V out 50%, right? And we also will learn about the energy efficiency, right? And then the sizing, sizing and area, right? So the goal is that we want to have the inverter that have the best PPAC trade-off, right? Always keep this in your mind. Any questions? Now, before that, let's take a look, right? Have a feeling on the physical structure, right? We always learn about the, we know there's a loading, right? But what is the loading? What does it come from, right? So on the right, I show you the layout. We have VDD, we have ground, and this is the poly, right? A traditional layout. This is input. And here is the drain. Here, here's the source, here's the drain, source, drain, right? And this is the output. The yellow one is the N well, which is the body for PMOS, right? And then the green one is the P well, the body for NMOS. Of course, we have contact, so the source is connected to the ground, right? And then the drain is connected to the output, right? So this is the gate. This is the drain. This is the source. Let's say it wrong again. This is the source. This is the drain. This is the drain. This is the source, right? So that's, if you compare to this structure, it becomes, this is the source. This is the drain. This is the drain. This is the source. If you remember, for PMOS, the source is at higher potential. For NMOS, the source is at lower potential, right? And based on this layout, right, if I try to do a cut horizontally, like here, I call this AA dash. How would it look like? This is PMOS, you will have something like this. I say this is N well, and we have the gate, and then we have the N plus, which is the source, not N plus, right? What should it be? What type of doping should it be for PMOS? Anyone?
P plus.
P plus, thank you. Right, P plus. Here it did not talk about the well tap, so I ignore it. And then here you have B dash, right? You have B dash. You have a P substrate, and then you have N plus, and this is the drain, this is source, this is the gate. Okay. In reality, in N well, we also have and also the P well, we also have a tap, well tap. Okay. That you will see it when you do the layouts for this assignment, right? You need to connect the tap, which is N plus, to ground.
Hey, Professor.
Yeah.
Why you have like A and A prime? I mean, why you need a different from left and right?
A prime, I'm just a cross section. I'm just saying that if I cut this layout, I cut into the wafer. This is the bird wheel.
Okay, so you basically just name the left side A and the right side A prime, right?
Yes, for this line.
I got it.
Yeah.
Yeah. Oh, you have like inverter, so you have a prime over there.
Oh, no. This is just the cutting, not about the signal. I draw a line, the line called A and A prime, not inverter.
Okay, thanks for explanation.
Yeah, I can call this AB and it becomes AB, XY, and this is XY. Okay, sorry, this is not clear. Right, so when I cut into this, I look into the cross section of the wafer, right? This is the bird wheel. This is the layout. And then it's just like I'm looking from the top. Is this clear? Don't hesitate to ask. I mean, some of us are not very familiar with this, right? If you ask now, then it'll be easier for you in the project. Okay, so what capacitance we have? I told you before we have 6 capacitance, right? 5 capacitance. I say it wrong again. CGS, CGD, CGS, I call it P, right? And then we actually also have a body. So we have a body to drain, which is CBD P, also body to source CBSP, right? Of course, we also have a channel capacitance, which is CGB P. Is this okay? We have 5 capacitance, right? So the total loading capacitance, of course, it comes from wire capacitance, right? And then if you look at this point, you have 2 other capacitance. One is CBDP, another is CGDP. But not just P, right? Also, we have that for the N, CBDN and CGDN. Okay, and then plus C input of the next stage. Actually, I discussed this last time already, but I want to see if you just refresh this idea. Any questions? And so when we do this, we are very detailed. We don't miss anything, right? Not hand waving. Yeah, in your interview, you may say, oh, I know there's a capacitance, loading capacitance, CBD, right? It's a total capacitance. But when you do your calculation, you really design your circuit, you need to know exactly what are the capacitance in order to optimize it. And by understand this cross section, you will know that in FinFET or SOI, how they are changing and how they are affecting the speed of your circuit. Questions?
Hey, Professor, I see you have a P at the end. Is a P referred to like PMOS, right? N refer to NMOS.
Yes, P refer to PMOS, N refer to NMOS.
Let me see the BD. Okay.
So here I will write, what do you call this? Can you tell me?
CGDN.
Yes. Yeah, thanks for helping. How about this?
CGSN.
Yes. And then again, we have a body contact, right? This is connected to ground. So what do you call this one?
The BSN.
Thank you. And the last one here?
And the BDN.
BN, yeah. Although it looks boring, right? And it's so easy for you, but I hope that at least you do it one time, right? And this is CGBN. Okay, so you can refer this to what we have learned before in the capacitors session. So you have 10 capacitors overall. Okay. If you understand it well, you won't think that that is too much. It's not difficult, right? 5. Okay. Now, then let's do a simple analysis. We call it first order analysis, but it's not that simple. First, we look at this. What is an inverter, right? When the input is high, VDD, then this is on, this is off, and the output is 0. And this is exactly what we have here. Okay, so when this is off, that is cut off, right? So you only have a resistor connecting to the output to the ground through Rn. So it means we need to find out what is Rn. This is first thing, right? Actually, we did that last time already. Then, when the VDD is low, the output is that this one will turn on, this will turn off, the output is VDD, right? Because now this is charged through the PMOS, right? And then we need to know what's our P, and the output is high. So very easy. Inverter is just like a simple circuit like this. So can you tell me, based on this, what is the VOH of this circuit?
VDD.
VDD. What is VOL?
Zero.
Yeah, thank you. Yeah, because the lowest we can go is when this is off, they will all discharge to 0. The highest we can go is when NMOS is off, then this will be charged to 0, right? How about VM? Can you see it?
VDD by 2.
Probably VDD divided by 2. Or you will say, I still don't know what is the size yet, right? Unless Rn equal to Rp at VM, right? So we don't know yet. Actually, I'm tricking you, okay? But that is a good guess. Good guess if you don't have any information. That is the best you can say, VDD divided by 2. So we are going to find VM. How about VIL, VIH? Do we know? Probably not. Now you know I'm tricking you. So no one answer. But thanks for trying. Yeah. Okay, so we are going to find that, right? So and then we also need to find the transient response, right? So based on this model, we know that the transient response is what? What is from low to high? First off, what does it mean? It means the time it go from V out, go from 0 volt to VDD divided by 2, right? So how does it transfer from 0 to VDD divided by 2 based on this network? I think you should know that, right? You already done the exam.
RP times CL.
RP times 0 is the time constant. How about the delay?
Maybe 0.69 times that value.
Yes, very good. Yeah. Okay, 0.69. And same from high to low is talking about from VDD to VDD divided by 2, right? We always say that it is 50%. So this one is going to be what? 0.69 RN CL, right? Is this clear?
Yes, sir.
Thank you. So you see that we just studied that. We say that the VOH is VDD. Okay, VOL is ground, right? So it's good. And so also another thing very important is that it has a low resistive path to connect from output to ground or to VDD. Okay, so if I have noise, I can pull it down immediately. So this is a very important point. Besides the regenerative, actually I should also add plus is regenerative nature, right? We talked about regenerative nature before, right? If you have noise in the VTC, it will just like this. Remember, it will just go up, down, up, right? It will just go to the VDD and ground, right? Another thing is that it has a low resistive path. So if I have a perturbation, for example, at this point, then it will be charged to ground or charged to VDD very fast. If it is not floating, or if it is floating, it doesn't have a low resistive path, then when you have a noise, it will just keep at that voltage. Okay, what is a typical MOSFET resistance? Can you tell me? Any guess? What's the typical resistance of a transistor when it is at on state? 1 ohm, 10 ohm, 100 ohm, 1000 ohm, 1 mega ohm?
1 ohm.
1 ohm?
Yeah.
Okay, any other value?
Wait, I'm thinking.
Yeah, you can do some intellectual guess also. Think about what voltage do you apply to the drain and what current it gives you.
I'm thinking that the VD sat is like typically what, 200 millivolt if we want to be amplifying,
Mm-hmm.
and GM maybe we want 20 millisiemens for 1 milliamp.
Instead of GM, how about the current? On current, do you know usually what is the value? It is about, let's say, 1 milliampere. And VDS now you say you can use VD set, but the order is similar, 1 volt, right? Usually your VDD is 1 volt, right? And then the current actually is in the order 1 milliamp, maybe lower. So this is about 1 kilo ohm. Okay, so don't think that it is too small, like 1 ohm. It actually is pretty large, but it is good enough, 1 kilo ohm, right? It may be a little bit higher even, or lower. Okay, so have this type of number in your mind will help you to make a lot of quick decision, right? Like in your company meeting, very fast. Instead of saying, oh, let me go back to do spice simulation. No one to wait for you, right? And you lose opportunity. Okay. The good thing is also it has 0 gate leakage current. It has 0 drain to gate voltage to ground leakage when it is at off state. Is this true based on your midterm and also the previous lecture? Is the leakage 0 from VDD to ground in CMOS?
I think no. I think they're always like current leaking.
Yeah, because of the
Sub threshold.
wonderful words now, right? Because of the subthreshold leakage. We'll talk about this later. How do you stack the transistor to reduce the subthreshold leakage, right? So we studied this class is actually to unlearn some of the concept you had before. The concept that's still too ideal that won't give you a job in nowadays world if you keep thinking there's no leakage. And indeed, nowadays, there's a lot of leakage. And that is what the whole industry is trying to avoid, to mitigate the effect. Okay. So let's start with